Okay, great. We're going to go ahead and get started. So welcome everybody to our fifth session of the afternoon. The session is Lock It Up, which is carbon capture opportunities and innovation. So in this session, we're going to be exploring both innovations within our high impact building materials like concrete and steel around carbon capture, as well as the carbon sequestering materials that are scaling to become competitive in the marketplace. The learning objectives for the session are shown here. And again, we'll follow up with a survey after the event on how to register for AIA credit. Regarding Q&A, so we're going to be collecting all of the Q&A that you submit. And if we're not able to get to it during the session, we will have our panelists answer it and we'll post that later on the CarbonPositive website. So with that, it's my pleasure to introduce our two speakers for the session. I'm going to keep their bios short so we have plenty of time for content and for Q&A. So first up is Will. Will Srubar is an associate professor of architecture and engineering and material science at the University of Colorado Boulder, where he leads the Living Materials Laboratory. Will also serves as the technical director of cement and concrete research and development at Katerra and serves as co-chairperson of the Embodied Carbon Network. Our second speaker will be Chris Magwood, Executive Director of the Endeavour Center. For the past 25 years, Chris has been actively helping reverse climate change by making carbon storing buildings that are also healthy, beautiful, efficient, and inspiring. And with that, I will pass it over to the two of you.
Great, okay. Thank you, Lindsay. I'm just gonna move to screen share here. Okay, thanks everybody for joining us. Will and I are going to be sort of trading off a bit during the presentation here. It's a slideshow, but I'm get us going in this session. It's called Lock It Up, Carbon Capture Opportunities and Innovations. And just to give the session a little bit of context, you know, if you've been tuning in at all today, you know that material-related emissions are quite large. The exact number, you know, can be debated, but essentially, you know, we know that these material-related emissions are something that we absolutely have to address if we're going to meet any of our climate change targets. And Architecture 2030 has certainly done a great job in all their work and with this event today to make that a lot more visible than it was even just a few years ago. So we know that it's this big problem, but we also know that we can't address it by just stopping building. There's more people, you know, being born every day. We're going to keep adding large amounts to especially our urban areas. We're going to have to retrofit our existing building stock to meet energy efficiency targets for emission reductions on the operational side. So at the very least, there's going to be a lot of materials put towards that. And we're also going to seriously have to think about the fact that we're going to have to house a lot of climate refugees and be doing a lot of reconstruction from storms and seawater rise and fires and things like that that are a result of climate change. So we know the emissions are big from building materials. We know we have to keep building and renovating, but we also know the urgency of reaching net zero emissions by, we could say 2050, we could say 2040, we could say, you know, but we know that the sooner the better. We need to get to net zero emissions. So essentially, if we spell that out, then it sort of follows that all new construction and renovations have to get to zero material emissions by 2050 or whatever date you want to sub in there. And we know that some building materials, at least for the foreseeable decade or two, are going to have emissions associated with them. We can't currently produce emission-free concrete, metals, glass, or a lot of other materials that we know are going to continue to be part of buildings. But what we can do is start making low carbon versions of these materials. And that's sort of where we'll start to dive in here. And we will let Will introduce you to that.
Yeah, thanks, Chris. So as many of you know, structural building materials, especially concrete, is a major carbon hotspot when you conduct a whole building LCA. But why is that, and how can we reduce that? What are the best practice strategies? So making concrete's a lot like baking a cake. So we take Portland cement, add water, there's a chemical reaction. We add coarse aggregate, fine aggregate, and supplementary cementitious materials like fly ash, slag, silica fume, metakaolin, even ground limestone or other natural pozzolans. And then we add some chemical admixtures. Really the secret sauce is to tailor the fresh and hardened state properties of concrete. Now we use these supplementary cementitious materials, or SCMs, for two reasons. One is to replace a proportion of Portland cement, and that helps with both carbon and cost reductions. But number two, really the main driver is that in most cases, the chemistry is such that it makes the concrete stronger and more durable through what's called a pozzolanic reaction of some of these materials with the byproducts of Portland cement and water, that hydration, to make more calcium silicate hydrate, or the glue, the good stuff in concrete. So really when we look at the ingredients to make concrete, the real carbon culprit is Portland cement. Next slide, Chris. Portland cement is certainly the most carbon and cost intensive constituent in concrete. Why is it so carbon intensive? So really, where does the CO2 come from? This is a schematic, what we're showing on this slide, of the kiln process used to make Portland cement. And at the very beginning on the left-hand side of the slide, you see that we take limestone that's in the ground, we quarry it and we crush it up, mix it with a little clay to get the right minerals and elements that we need. And then we start to heat these up together in this kiln process. And what happens is that at the very early stages of the process, the limestone that we use undergoes what's called calcination, meaning we take calcium carbonate, which is limestone, we heat it up, and off goes the CO2 that was bound in that carbonate mineral. And if you take a look at this process from a holistic standpoint, about 50% of carbon emissions associated with cement production is attributed to this calcination process, this chemical reaction of driving off the carbon dioxide from limestone. As we continue to heat the limestone and the clay together, you can kind of see further down the process line that another 40% of the carbon emissions comes from the fuel combustion that is necessary to heat the kiln. And as we go further down the process, as we start to blend it and grind the cement, and ultimately transport it to ready-mix plants, that about 10% of the carbon emissions are associated with transportation. So if you think about decarbonization of the electric grid, we can probably address about 50% of the carbon emissions with better fuels, renewables integration, with fuel combustion and transportation, switching to renewable energy sources. But really, we can't get around the 50% emissions of the limestone calcination. So that's a pretty gnarly problem that's being faced by the cement industry. And we are looking at carbon capture technologies, but in order for this to be effective, there has to be a carbon capture system on every cement plant around the globe. And that's really an inefficient and really a scale issue that we're facing right now. So really the principal carbon reduction strategy that most designers and decision makers have looked to is to use less cement. And if we go to the next slide, Chris, how do we implement using less cement in practice? How do we get across that we want to use less cement? So number one, one way to do it is to edit master specifications to specify design compressive strengths at later ages other than 28 days. So specifying 56 or 90-day compressive strengths where you can. And why it works is that concrete continues to gain strength with time. We know from the material science standpoint that the 28-day compressive strength convention is really outdated. And many concrete mix design submittals will have what's called a 3-point curve, a strength development curve that you can take advantage of and select mixes that may have gain sufficient strength at later ages. So of course you need to balance this with scheduling needs of getting early age strength to move along on the construction schedule, but really this is a really great strategy that folks are implementing. Number 2 here is to specify a minimum supplementary cementitious materials replacement. This really gets at replacing part of Portland cement, a minimum threshold of that. And I already explained that there are a bunch of benefits of doing this. One thing that I will note is that, right now, if we look at the embodied carbon calculations for concrete, the product category rule, how we attribute the emissions of fly ash and slag, are such that we don't account for previous emissions associated with coal combustion to get the fly ash or steel making to get the slag. The only thing that we account for is transportation. So because there's higher value in these materials, we are going to have to start paying attention to this in the future, and perhaps the PCR definition should change. I believe it actually should change in the future. So we just have to be careful about this particular strategy going forward if previous emissions are associated with SCMs. Number 3 is specifying a type 1L or an LC3 cement. This may be familiar terminology to some, maybe unfamiliar to others, but a type 1L cement is a normal type 1-2 Portland cement that has up to 5% ground limestone that replaces Portland cement. LC3 is a limestone calcined clay cement, which replaces up to even higher percentages of the Portland cement. And studies have shown that you can do so without compromising any of the performance of the concrete in the early or late ages, thereby reducing your emissions. If you go to the next slide, Chris. What I wanted to do, just as a quick summary, so Chris and I were part of a consulting project, and we presented this to the client, but this demonstrates the reductions that are achievable by implementing those 3 best practices by using a concrete mix that exhibits a 4,000 PSI design compressive strength. All of these mixes here will ultimately meet that design compressive strength of 4,000 PSI, but you can see that the different levers that we pull, switching from 28 days, for example, to 56 days, or switching from a lower, from the first and second, the differences between the first and the second row here, going to higher SCM contents with up to 50% slag, moving then to a later age design compressive strength from 56 to even 90 days, going above 50% slag, and even using a type 1L cement. Just those simple strategies that you can implement today could result in substantial, we're talking 50% reductions in embodied carbon of concrete that are really achievable today. One thing that I will mention is you may get some pushback. Some contractors might bellyache a little bit about using high SCM replacements because of workability issues and even set times, but those are things that can easily be overcome with just adjustments in the schedule, or even some admixtures that could help accelerate the early set times of the concrete. Chris, if you go to the next slide, the 4th strategy I just wanted to mention really quickly is in your master specifications, architects and engineers can specify limits in cement contents for different compressive strength categories. So specify a cap for your 4,000 PSI concrete, specify a cap for your 6,000 PSI concrete in cement content and or embodied carbon. And what this really does is it forces the hand of the supplier to use performance-based approaches to get a mix that meets your specification. And if you're looking for model language to amend your specifications, I'll point you in the direction of the Marin County Building Code the low carbon concrete building code that many of us who've talked today had a hand in architecting really as model code language. If you go to the next slide, Chris, you know, I wanted to mention that because those are huge reductions that are achievable today for concrete. You know, we're working on other strategies that we'll highlight throughout the rest of this presentation. And we're working on other strategies to decarbonize steel through electric arc furnace, steel making, and really circular economies of steel and recycling structural steel, and even with glass manufacturing. If you go to the next one more bullet, Chris, you know, the moral of this story though is at the end of the day, these materials and even these strategies will still result in materials that have net carbon emissions. And at the end of the day, low carbon isn't zero carbon. Emissions are emissions. So in order for us to build buildings that have net zero carbon emissions, we must look to strategies that enable us to store carbon in our buildings and have utility with products that have negative emissions that really store carbon through their manufacturing process. And that's what we're going to talk about through the rest of our time here today with carbon storing materials. Chris, I think it's back to you.
Great, thanks, Will. That's a great overview. I think a lot of times, you know, concrete is pointed at as sort of the bad guy, but a lot of people don't know why. That was great to have it put that precisely. But yeah, the rest of the time we are now going to talk about the materials that actually can store carbon in your building. And essentially there are two ways or two sort of product types that can do this. One is products that are putting the CO2 in the product via photosynthesis. So these are the plant-based materials. And then there's also carbonate mineralization, where atmospheric CO2 can be drawn down and sort of remineralized. And so we'll be looking at both of these types. And we'll be starting with the photosynthetic carbon storage. But to give you a sense of what that means, because it can be hard to figure out sort of what these negative emissions or what this carbon storage actually means or what it looks like. So we've tried to represent it sort of graphically here for you. So, you know, here's a graph with carbon storage on the lower side and emissions on the higher side. And if we're thinking about the plant-based building materials, although the carbonized mineral materials would follow a very similar graph here, there's usually some amount of emissions associated with first planting a material, whether it's reforesting or an agricultural crop or a purpose-grown plant crop. So a little burst of emissions from planting it, and then a period of that photosynthetic drawdown. So as this plant grows, the time scale here could be anywhere from, you know, 3 to 4 months for something like wheat straw to 40 to 60 years for timber. But whatever that time scale is, over the life of that plant is actively taking CO2 out of the atmosphere and using those carbon atoms to essentially build its structure. And most plant-based materials, it varies, but somewhere between sort of 40 to 50% of the weight, the dry weight of that plant material is going to be carbon, and all that carbon came out of the atmosphere. So in growing, that plant has stored carbon. There's less CO2 in the atmosphere at the end of that plant's life than there was when it started growing. If we're going to turn those plants into building materials, there's going to, if you're familiar with your LCA work, these will seem familiar, but we have to harvest that plant. We're going to manufacture it. We're going to transport it. We're going to construct it into a building. So at all of those phases, there will be emissions associated with that. So you can see the carbon levels rising again. But with all the plant-based materials that I've ever studied, those emissions tend to be significantly less than the amount of photosynthetic drawdown. So, you know, the actual amount varies material by material and process by process. But the bottom line is, once we've actually put that material into the building, there will still be less CO2 in the atmosphere after we've put that material in the building than there was before it started. So the amount of carbon, the net carbon after the photosynthetic drawdown has brought it down out here, and after the production and construction phase have put a little bit back, for the lifespan of that building, that carbon stays in the building. It stays out of the atmosphere and is not driving more climate change. And then, of course, at the end of that building's life, and the length of that line is really important. The longer that we can keep that carbon out of the atmosphere and in a building product, the better. But at the end of that lifespan, there's a whole bunch of ways that we can deal with that carbon. Ideally, we would reuse it. So this is designing for dismantling, so that that carbon-based building material at the end of one building's life can actually just be put into another building. It could be recycling it, so taking it apart and turning the constituents into other products. It could be turning that carbon into biochar as a soil amendment or a further building product, combined heat and power, landfill. And depending on the landfill scenario, some of that carbon may be stored long-term in the landfill. It might actually create more methane, in which case at the end of the product's life, there could be a little burst of emissions. But if we're smart about it, that carbon stays out of the atmosphere for a good long time. And if we look at any non-photosynthetic building material, so almost all building materials that aren't plant-based, their emissions profile is completely the opposite. Every part of that emissions profile is on the emissions side of the line. So from harvesting through manufacturing, transporting, and constructing, all of that is producing emissions. And so that looks very different, that while the material is in that building, it has caused emissions, and those emissions aren't just in the atmosphere the year that those materials are made or the year that building is made. They continue to be in the atmosphere for a long time. So they continue to sort of add to the radiative forcing long after they've at first been emitted. And so what we end up with is photosynthetic materials that offer, meaningful carbon storage until at least 2050. I would hope by now any building that we're designing has at least a 30-year lifespan, whereas all the emitting materials, they've put CO2 in the atmosphere. And so the difference between sort of that red line and the green line is the difference when we sort of talk about negative emissions or carbon storing materials. They're the ones that for the lifespan of the building are below that zero emissions line. So what kinds of materials are there that's using this kind of atmospheric carbon? They kind of fall into four categories. The plant-based materials are things like bamboo, hemp, rice, straw, cork, seaweed, bagasse, cornstalk, algae. There's a litany of plants that can and are used in buildings and have been historically and continue to be now, and a lot of work going on with sort of new and innovative ways to use those materials. And timber, although it is a plant, is sort of in a category of its own, and we'll talk about that in a little bit because of the time it takes for timber to grow. So all those plant-based materials are quite short cycle, either annual or as much as 6 to 8 years to grow and be renewed, whereas timber is on a sort of multi-decade timeline. So it's a little bit different in how we would think about the carbon that it contains. And then there's a lot of waste stream carbon. There are a lot of things that weren't made to be building materials initially, but that are plant fibers that at the end of their life typically either get sent to landfill or get incinerated, and that carbon ends up back in the atmosphere. So that could be things like paper and cardboard that can be made into cellulose insulation, rewall that's made from drinking box containers, wood fiber insulation that's made from mill waste. So there's a whole bunch of things that weren't made to be building materials, but by making them into a building material, they keep that carbon out of the atmosphere. And then there's the whole category of manufactured minerals, which we'll deal with a little bit later. But no matter what category of these that you want to consider, and you probably want to be considering all of them, in order to make a building that actually has zero net emissions, we know that we're going to use some materials that are going to cause emissions. So if we want our net to be zero, you have to build with at least enough of these carbon storing materials to get your total down to zero. So really, you know, these types of materials have to be part of any zero carbon strategy, because there's no way to get to zero carbon without these materials to offset the ones that are causing emissions. And so just a reminder here that when we're talking about biomass, when we're talking about plant-based material, typically 40 to 50% of that biomass is stored carbon. So, you know, when you start to look at stocks and reserves of things like agricultural residues and forestry products and bamboo and all of these other things, a great deal of that weight, the sort of actual biomass, is that carbon. And Will, do you want to talk a little about mass timber?
Yeah, thanks, Chris. And as Chris said, you know, if you take that into account, you know, all the biomass in trees, plants, leaves, stems of plants, you know, half the mass of it is stored carbon dioxide. So if you have 2 tons of biomass, it's 1 ton of stored carbon dioxide. And the best example that we have right now, you know, most people default to timber and engineered wood products, but mass timber really is usually the only plant-based material that's considered. As Chris kind of alluded to, there's a difference in the cycles of growing these materials. So right now, it's actually very difficult to verify the carbon storing value of timber products, just because that we have to guarantee that it's from a sustainably harvested source and that biomass is replaced every year. So if we're trying to increase our use of these materials, we have to increase the number, really the acreage of sustainably harvested forests, and replace that in a sustainable way. So it is a little bit more nuanced than say these agricultural materials that have annual cycles of regrowth. The biomass is replaced every single year, rather than 20 to 30 years as mass timber, like mass timber. So really, in other words, sustainable forests are already grown and harvested to make the products, so to keep increasing forest product production while maintaining the carbon sequestration value of the forest, we need more tree stock in the forest ecosystem. So what Chris and I really want to unpack, though, and I hope you walk away with this takeaway, is thinking about other types of materials. Really, is there another way? Is there another set of materials? Chris, if you advance the slide. And there was this really great study put out by Yale School of Forestry this year on buildings as a potential global carbon sink. And this did highlight the utilization of mass timber and engineered wood. But what I thought was a little bit short-sighted in the study was the huge opportunity to use other plant-based building materials that are already at scale and are becoming more and more available. We have such an opportunity to increase that potential even further. Chris?
Sure, and actually I might just go back, you know, in my own work, and we're gonna look at some straw-based systems, but if we think about the stocks of these agricultural byproducts that are out there, every year there's 2 billion tons of grain straw grown on the planet. And that means that plants, just the grain plants that we're planting every year, that farmers are already planting and already harvesting, the leftover straw from that has drawn all the CO2 that was emitted by transportation on the globe. It's all been drawn down and stored in grain straw. We're just typically either burning that straw at the end of the season, or in some way letting it rot, molder, compost, or go back to the atmosphere. So you know, as you look around at all of these stocks, the potential there is really huge. So what I want to do is just sort of focus, because there are so many different materials that we could examine, and our time is too short to do that. What I really want to do is over the next couple of slides, look at ways to do panelized construction using these carbon storing materials. And the reason I want to focus on panels is because not only does a panelized system offer a way to use a lot of carbon storing materials and to put them sort of in an affordable and accessible format, but because panelized systems can be designed so that they can be easily dismantled and reused at the end of the lifespan of that building, it means that we sort of get this potential to keep that carbon stored for longer than the lifespan of a single building. So there are many ways you could be using these materials and many types of these materials that aren't panelized, but we'll just look at some panelized systems now. And panelized construction is going on at all over the world at all kinds of scales. From this very small scale, the little building school where I work, we made this little panelized house that included Velos panels, some cork panels, and a panel up there on the top left of your screen that uses mycofoam as an insulation grown right on the straw panel. So all kinds of different ways that these materials can be panelized and used, meaning that a little house like this, even though it's got metal siding and metal roofing and obviously glazing and lots of materials that had carbon emissions, the net carbon storage of this little 1,100 square foot house is 250 kilograms of CO2 per square meter of that building. So this little building has about 24 tons of carbon, net carbon storage in one little house. And that works at all kinds of different scales. So in France, the Jules Ferry residence is a 7-story, and also using prefabricated straw bale panels, but on a larger scale. And their calculations showed that they were having 800 kilograms of CO2 storage per square meter of that building. So, I know that one of the things that always comes up when we talk about these materials that sort of have a reputation as being like the alternative materials is, well, yeah, but can it work at scale? And, I think there are some projects like this one that show that indeed it can. It's more a matter of will than the actual ability to do it. And there are all kinds of ways that that the structural and insulation side of the panel business can be done with carbon storing materials. So we've showed you some wood frame and straw options, and there are several companies, EcoCocon, ModCell, Tooktree, and a bunch of others in either production or startup phase around the world that are doing this in one form or another. There's also wood frame and hempcrete panels, and again, resulting in net carbon storage, and American Lime Technologies and Hemcore and IsoHemp and others are going down that pathway. And then, in a lot of ways, a lot more conventionally, there are wood frame and cellulose insulation panel systems, and actually starting to be, adopted and made a lot in different parts of the world. In the US and Canada, Benson Wood, Phoenix House, Tooktree, Simple Lifes, Barrett. There's a whole bunch of companies that do carbon storing panels with that set of materials. Also, things like structural bamboo panels, where the bamboo is a hollow core structural member, and any carbon storing insulation that happens to be regionally produced can be used as insulation in that system, and again, resulting in net carbon storage. So there's a whole bunch of different ways. There is more than what we're showing you here, and more different materials, but just to give you a sense that this is a field that is both in development and in use, but also I think at a point where adoption is sort of ripe to expand and really grow, and to bring these types of carbon storing materials to the market at a lot larger scale. So in addition to structure and insulation, there's cladding materials. So there's some really interesting hemp composite materials, rice hull composites, cork, charred wood, bark, thermally treated wood. So again, a whole range of products. This isn't an exhaustive list by any means, but further ways to sort of take the notion of putting carbon storing materials onto buildings and upping that net carbon storage. And the interiors of buildings offer a huge potential here. I know one of the questions about carbon storing materials comes when people think about them as, you know, how do they apply to very large buildings where, you know, clearly it's going to be harder to make them an integral structural part of a really tall tower. But those buildings have vast amounts of interior space where things like sustainably harvested wood, bamboo, sorghum, and other types of biofiber panels can be used as interior finishing. There's a lot of companies that make a compressed straw interior partition wall system. So it's a thick panel that goes in a C channel and is both soundproof and fire retardant, simple to install, but also makes changing those buildings around and modifying them really easy. Rewall, we mentioned earlier, wallboard and ceiling tiles from recycled drinking boxes. Wood wool panels have actually been around for a really long time and are another great interior material for carbon storage. And again, nowhere near an exhaustive list, but just to give you a sense that, you know, the opportunities to put these kinds of carbon storing materials to use in buildings is, it's everywhere. It's all through the entire building cycle.
So I wanted to talk a little bit about mineralization. So Chris and I just talked about one of the strategies for storing carbon in materials, and that's through photosynthesis, trees, plant-based materials. The other way that we mentioned was through mineral carbonation. So what I'm showing here is many folks are familiar with CarbonCure, the concrete technology that injects CO2 into fresh concrete mixes. This leverages mineral carbonation in its technology. So in a nutshell, CO2 is injected in the fresh state of concrete. The CO2 reacts with the calcium that is in the system from the Portland cement that's hydrating, and that produces calcium carbonate. And you know, many people have certainly viewed this as a way to reduce embodied carbon of the concrete mixes. And certainly there's a lot of data out there that with the benefits of utilizing CO2 to reduce, really the benefit is in the cement reduction that's possible through this approach. There are some limitations to this approach. So number one, there is limited success with low strength, low cement content mixes. So if you have a really high SCM mix, the chemistry just doesn't necessarily work as well. And then, you know, the utilization of purified CO2 and the fact that, you know, the CO2 doesn't really add cost or any durability benefits are really limitations. So those, you know, the main takeaway for CarbonCure is that it is great. I think it's a good technology, but really it's only somewhere between 5 to 10% reduction that is achievable. And so there's really no significant carbon storage. And I really would recommend to clients that the best practices that I discussed earlier result in much greater carbon reductions if you're looking for that. Next slide, Chris. Another company that is leveraging carbonate mineralization is Solidia. So Solidia takes a mineral called wollastonite that's mined from the ground and reacts that with carbon dioxide and water. And what results is a carbonate-based cement and a product that acts and feels like precast concrete. There is a limitation to wollastonite and carbonation approaches that Solidia uses, in that only about 1.5 million kilograms of wollastonite are mined each year in the United States. And we actually make 100 billion kilograms of Portland cement every year in the United States. So it's really a scale issue that they're facing in advancing this technology, but it is available and on the market today. Next slide. two more technologies I wanted to mention have to do with a different approach than CarbonCure and Solidia, because CarbonCure and Solidia really are focused on Portland cement replacement. But what I want to talk about are two technologies that are looking at the aggregate as a way to store carbon in concrete through carbonate mineralization. So this is a graph that is showing a volumetric cubic meter of concrete, and aggregates, sand and coarse aggregate account for 90% of the volume. Portland cement accounts for very little, anywhere from 5 to 10% of the volume. But if we look at the CO2 emissions associated with each of those constituents, Portland cement production accounts for 95% of the CO2 emissions. So what I want to highlight is that there's a grand opportunity to look at limestone aggregates, not ones that we crush up out of the ground and use out of the ground, but ones that we manufacture as an opportunity for carbon storage. Chris, next slide. This is the technology of Blue Planet. So Blue Planet is trying to, in essence, grow carbonate aggregates utilizing waste sources of carbon dioxide and waste sources of alkali. So it's a chemical approach, and they're trying to create calcium carbonate coatings on recycled aggregates that can then be used in regular concrete. I just showed this graph here, this last little row that shows that with about 30% of a carbon storing aggregate replacement of our coarse aggregate, we can get to a carbon neutral concrete. But it's not through Portland cement reduction or injecting CO2, it's actually looking at the aggregate and making an aggregate from the limestone, or making limestone aggregate from waste CO2. The last thing I'll mention, if you go to the next slide, is a technology that my lab is developing, similar to Blue Planet, but Blue Planet uses a chemical approach. My lab is using a biological approach to grow limestone aggregates using photosynthetic organisms. So these are examples of stromatolites. These are natural limestone formations that marine cyanobacteria nucleate and grow in certain parts of the ocean. If you go to the next slide, Chris, what I wanted to show is that in my lab, we're growing tiny little stromatolites. We're growing tiny little limestone particles using these bacteria. So this is a flask here, a green flask of these photosynthetic organisms. Using artificial seawater, we're able to get the bacteria to use CO2, nucleate a limestone crystal, and in effect grow limestone that we could then use as a filler or as an aggregate replacement in Portland cement concrete. What's great about this approach, and even with Blue Planet, if we look at maybe a limestone filler replacement of Portland cement at around 5%, we actually get a 10% carbon reduction, because we're not only replacing Portland cement, we're using something that was grown using waste sources of CO2. So we get double the benefit, really double for our money here. Next, final slide, Chris. I think this is the last slide that we have to share with everyone.
Yeah. So the wrap up here is that if we do want to get to carbon storing buildings, or at the very least to carbon neutral buildings with zero net emissions, how do we get there? Well, first we have to engage in measuring the emissions in the first place. And I think, today's talks, and especially the tool demonstration that have been going on, have been a great place for people to start seeing, how that's possible, where it's possible, what tools and calculators are out there. And then we have to set real targets with the whole team on board, so that everybody understands the importance of doing this. And I hope all of today's presentations are really driving that home, and understanding sort of where the building that you're designing, where the baseline for that building is or could be, and then go about doing better. And even though we showed some buildings that have sort of net carbon storage right now today, it doesn't mean that everything has to, jump there right away. There can be a period where you focus on reductions. And if you think about it, if you can reduce 10% a year for 10 years, you should be at a zero net carbon building in a decade. So, set yourself realistic targets, and then really make sure that you're hitting them. And I think really important is to innovate. We've showed you a super quick glance here at a lot of innovative materials and approaches. So learn more about them, check them out, find them, learn how to use them. But support those innovators, take some of the risk that it might take to use those innovative materials, and then make sure that you are designing for disassembly and reuse, so that if we are making buildings that do store carbon, that carbon is locked up beyond a single use in a building. And know that it might not be easy to do this, but it is absolutely necessary. And we know from existing examples right now that it is doable. So it's just going to take everybody getting on the path to making it a reality.
Great. Thank you both. We're unfortunately right at our time. So I'm going to have to leave to start the next session, and I'm going to go ahead and conclude this session. However, Will and Chris, if you're able to stay on and answer some questions, I believe you'll be able to do so. But with that, I hope to see all the attendees on our next session. And thank you, Will and Chris, so much for a wonderful presentation and really incredible insight.
Yeah, thanks for the invitation.
Yep.
Yes, thank you.
Yeah, I think we can answer a few questions if folks want to stay on. One I did want to mention is Nathan brought up a good point about the approximate 10% Portland cement, the type 1L Portland cement does actually account can accommodate 5 to 15% of limestone, ground limestone. So the rule of thumb is about 10%. I like to err on the side of be a little conservative with the 5% number, but you're absolutely right. We can get higher percentages in the type 1L. There are some questions. I think one question about getting these to scale. Chris, maybe you can comment on getting contractors comfortable with the installation and use of these innovative products, since you encountered this a lot in your practice.
Sure. Yeah, and I guess that's part of the reason that I focus so much on prefab components, because I definitely understand that, taking a material that you're not familiar with as a single component and figuring out how to source it and install it and service it and all of that can be really difficult. And so the reason for focusing on panelized systems is that it doesn't take the whole crew understanding how to say work with straw or work with hemp or work with another material. It takes a knowledgeable manufacturing facility that can then send you a building component that installs like any other panelized building component. So I think part of the reason for focusing on the panelized systems is that it doesn't really matter in a lot of ways what that panel is, whether it's a big slab of CLT or a precast concrete panel or a radical straw bale panel. Essentially the way those things handle, the way they're craned, the way they're fastened really follows a pretty similar methodology. So I think when we think about trying to scale these things up, that's why I'm really hopeful about panelization, because it doesn't require a sort of vast retraining or a whole new set of supply chains to get those individual materials to everybody's site and installed. Instead, it just takes good manufacturers providing a product that almost anybody can install.
Thanks, Chris. Is there a good central resource for those types of these carbon neutral, carbon storing materials, and perhaps one that may be in the works?
Sorry, you froze there, so I didn't get that whole.
Yeah, is there a good central resource for learning more about these carbon neutral materials, and maybe even resources that are in the works?
Sure, yeah. There is a book that Bruce King and I are working on that should be out next spring, which is going to be all about these materials. The Renewable Materials Task Force of the Carbon Leadership Forum has a lot of good resources. Builders for Climate Action and the Endeavour Center also have lots of resources about carbon storing materials. So I would say those are all good places to start.
Great. There's one question about speaking to the differences between mass timber versus dimensional lumber stick frame construction. I think just by definition, they're pretty similar. So mass timber is made up of pieces of dimensional lumber that are laminated together at 90-degree angles to sort of make a composite. And so, you know, structurally speaking, you can rely on many of the same properties of dimensional lumber to get this larger layup, you know, higher stiffnesses and even to some degree some higher strengths, utilizing stick frame, you know, dimensional lumber. Now, I think in terms of carbon storage, you know, if you're looking to build the same building out of mass timber versus stick frame, I think it actually comes down to the economics versus the carbon storage potential. There's a sweet spot really with where mass timber makes a lot of sense with it being the main structural system versus stick frame. Chris, I don't know if you have any additional comments on that.
Yeah, I think in a lot of ways it is a scale issue. You know, you can only use stick frame because there's a lot less wood and therefore a lot less structure at a certain scale. And once you get beyond that scale, a stick frame just isn't going to have the structural capabilities to do what mass timber can do. So, you know, it's here in my part of the world, we can stick frame up to 5 or 6 stories. But if we want to use timber and we want to go beyond that size, then we're going to be relying on mass timber. Now they can be combined. You might be able to use, say, a mass timber floor and shear wall system and still use, say, some stick frame components like stick frame exterior cladding walls. So there, you know, it's not a sort of one or the other thing, but I think it's largely just a case of scale in terms of which way you would go.
There's a question for you, Chris. What do you mean with doesn't have to be all at once, 10% reduction a year for 10 years? Are you referring to interior materials? How do you suggest doing this 10% reductions per year for the structure?
Well, I mean, I think, you know, we've already pointed in this presentation, you know, Will showed some really practical ways that even a high emissions material like concrete can be reduced by up to 50%. So, you know, if you're able to slowly introduce better concrete into your projects and start combining it with carbon storing interior materials, start combining it with some carbon storing exterior materials, you know, I think, you know, what I was trying to say there is, you know, there's a certain level of discomfort with, you know, a really radical change. Like if everything about your building changes, the concrete changes and the framing system changes and the insulation changes and the glass changes, you know, if you do all of that at once, that's a tough project to pull off. But if you can, you know, strategically set yourself some goals, figure out how to get, you know, 10% less, and then the next building figure out how to get 10% less than that, and the next time out get 10% less than that, then, you know, within a decade you're starting to, you know, creep close to that zero line. And I think, you know, at that scale, that's a very approachable way to do it, rather than saying, well, we have to throw out, you know, everything we know and everything we're familiar with to get to zero tomorrow. We have to get to zero pretty soon, but you don't have to do it all in one building right away.
I think we'll take one more question here, and that has to do with reusing plastic or other quote unquote waste or garbage versus maybe competing with growing food for growing building materials. You know, are there toxic problems? Is it too difficult to overcome to use waste materials? Maybe Chris, have you encountered other waste materials other than cardboard and plastics. I know I could probably speak to this a little bit as
Yeah,
well.
well, I think the first thing I'd like to speak to is the notion about competing with growing food. I really, there's no way that I would advocate, devoting land use to just growing building materials. I think the beauty of the materials that we focused on in this presentation, the plant-based ones, are that the building material part is using the residue from the food product. So like I said, we grow 1 billion tons of grain every year to eat. And in growing that 1 billion tons of grain, we grow 2 billion tons of grain straw that holds that seed up. So, I'm not advocating that we, cut down a bunch of forests and just plant straw to grow as a building material, but that we're already growing that straw and we're just not using it. And same goes with almost all of those agricultural residues. So that combined with plant-based materials that can be grown regeneratively. So if you think about, say, like the bark of cork trees, so those trees, the bark is regrown on an 8 to 10 year cycle and harvested from the same trees for hundreds of years per tree. So, and same with bamboo, the right types of clustering bamboo can be grown on a 6 to 8 year cycle on the same land, so that, the last thing we want to do is encourage deforestation or land use change to grow building materials. But what we want to do is really effectively use the material that's already being grown and isn't currently, we're just not using that plant-based material for building materials, or really for any other reason. It's just going back to the atmosphere.
And I would second what Chris mentioned about leveraging the agricultural residues to make materials versus relying on other sources of waste like plastic. There are certainly some leaching concerns and some long-term stability concerns with plastics, especially in regard to fire retardants. And so I'm hopeful that we'll have engineered a way to recycle plastics back into other plastic products versus having to just try to store them in buildings. I do hope that we are leveraging the agricultural residues that already exist, because those arguably have a little bit more better from a material property standpoint and toxicity standpoint than many plastics. So with that, I think I'm going to conclude this session. I really thank all of you for tuning in, and especially for engaging in the Q&A here at the end. Feel free to contact Chris or me if you'd like to have continued discussions, but I hope you all enjoy the rest of the day.
Yep, thanks. Bye.